So 8 times 35 is 280. Divided by 14 is 20. So this is 20 here. Over here we have 15 times 35, which is 525 divided by 21 is not 5, it is 25. What's that? Yeah, 25. Now over here, since it's x plus 5, it's easier to do a full cross multiplying. So 18 times 15 is 270. Over here, x plus 5 times 27 is 27 times x plus 5. And we'll distribute the 27. So 27 times x is 27x. 27 times 5 is 135. We then, what do we do next to solve for x? Minus 135. So 135 equals 27x. Then divide by 27. 5 equals x. And then over here, we do the same thing. We cross multiply. 16 times 15 is 240. Bless you. 3x times 20 is 60x. That's a common disease going around lately. So then we divide by 60 to get x equals 4. Any questions? Okay. Well, okay, so what we're going to talk about today is called variation. And variation ties in very tightly with the proportions we did yesterday. Proportions actually describe a certain type of variation, and that is direct variation. In direct variation, if the value of one amount, we're going to call it the x amount, gets larger, the value of the other amount, which we will call the y amount, also gets larger. Or the other way around, if the value of the x amount gets smaller, the value of the y amount must also get smaller. Direct variation is symbolized in a couple of different ways. One of them is as a constant ratio. Usually put it as y over x, not x over y. Y over x equals a constant. The ratio between y and x is a constant. The other way it can be written is that y is equal to that constant times x. Now, what we did up here, that y divided by x equals a constant, is actually where our proportion comes from. You know, he went 46 miles on 2 gallons of gas. That gave us that ratio of 46 miles, actually a rate technically, on 2 gallons. Then if we want to know how far would you go on 5 gallons, well, this ratio has to equal that one. They both equal the constant, so they equal each other. But we could also have used this equation here. Let me show you what I mean. So 46 miles would go in for y. It's a constant times our 2 gallons of gas. We could figure out what k equals. How would we figure out what k equals? Well, it's k times 2, so to solve for k, we would divided by 2. 46 divided by 2 is 23. So K equals 23. Now if we put units in there, remember that's 46 miles equals K times 2 gallons. So what we're really dividing by is 2 gallons. So 46 divided by 2 is 23, but it's technically miles per gallon. So that constant we're getting there is our gas mileage in this case. So we know that y equals 23 times x. The next piece there, we asked how far would we go on 5 gallons? Well, y equals 23 times 5. So y equals 115. So that direct variation is something we're relatively used to. We might look at a direct variation. One big example of direct variation would be a map. Let's say on a map, your scale says 1 inch equals bless you, 50 miles. And you look on the map, your two locations, for lack of further creativity, we're going to call them A and B, are 2 3/4 inches apart. To find that distance, we set up a direct relationship. 1 inch is 50 miles. Could I have done 50 miles over 1 inch? Sure could. Equals, where's the 2 3/4 have to go? Has to go wherever the other inches are. In this case, that's on top. So 50 times 2 3/4 divided by 1 is 137.5 miles. Is that what we come up with? I believe so. So that's direct proportion. Another example of direct proportion, something called mechanical advantage. A mechanical advantage is your ratio of output force to input force. How do you create a mechanical advantage? One of the simplest things you can use is a lever. So let's say we've got something to balance on there. Now let's do this. Let's say we've got a big rock we need to move, and we can't make it move. You can set a thing to balance on there. It's called a fulcrum. And you can take a board or lever and put it on there. Now the mechanical advantage is equal to the distances. Let's say that this is 20 inches. This is 60 inches. Your mechanical advantage is going to be 60 inches over 20 inches. That would reduce to both divided by 20, a 3-to-1 mechanical advantage. So if we apply a force here of 200 pounds, how much force is coming out here? Yeah. 200 pounds is the smaller amount, so it goes with the smaller number. We cross multiply. 3 times 200 divided by 1, we get 600 pounds of force out of it. Does that make sense? So those are direct proportions. Direct variation. The second type is called inverse variation. Inverse variation are values where one value gets larger, means that the other value gets smaller. Or the other way around. If the X value gets smaller, the Y value has to get larger. For example, let's say you are going on let's just say a 360-mile trip. If your vehicle gets 24 miles per gallon, you're going to use a certain number of gallons of gas, right? How much gas would you use? Well, 360 miles divided by 24 miles to the gallon, right? That's going to give you 15 gallons of gas. Let's say your mileage increases to 30 miles per gallon. Is the number of gallons used going to get bigger or smaller? Smaller. Your mileage got larger, the gallons used has to get smaller. 360 miles over 30 miles per gallon is only going to use 20 gallons. Or 20. I screwed something up there. What does that come up to be? 12, right? 12 gallons of gas. So how does this relationship look? Well, the typical way of expressing this relationship is x times y equals a constant. Or you can express it as y equals a constant divided by x. But typically we express it as x times y equals a constant. Over here it is mileage times gallons equals the constant. Your mileage of 24 miles per gallon times 15 gallons, that has to equal what you would have over here at 30 miles per gallon times 12 gallons. So if we were setting this up, let's look at another example. Let's say we're going 300 miles on a trip. Well, let's not even do that. Let's forget about the number of miles on the trip. Let's just say in a vehicle that gets 20 miles per gallon, the trip used 15 gallons. How much gas to be used if the mileage were increased to 25 miles per gallon? So that relationship is your mileage, 20 miles per gallon, times 15 gallons, has to equal 25 miles per gallon times X gallons. How do we solve for X? Well, 20 times 15 is 300. We divide by 25. That would give us 12 miles per gallon, or 12 gallons of gas for that trip. Probably the biggest application of inverse variation in mechanical side of things is your gears and your pulleys. So we've got a 6-tooth gear here meshing with a 10-tooth gear, right? Helps if I write them in the right spot. 10 teeth, 6 teeth. If that 10-tooth gear is running at 240 revolutions per minute, RPM, what's the RPM on the 6-tooth gear? Does it have to be larger or smaller? the number of teeth went down, number of teeth got smaller, the RPM will get larger. Because if you think about it, this gear here, the 6-tooth gear, makes one complete turn. We've only gone 1, 2, 3, 4, 5, 6 teeth on the other gear. We've only made it 3/5 of the way around. So our gear ratio here is depending on which one is which, would be a 6-to-10 or a 10-to-6. But what we look at here, it's the number of teeth times RPM has to be a constant. So for the first one, there's 10 teeth times 240 RPM. That has to equal 6 teeth times that RPM. We'll call that X. Well, 10 times 240 is 2,400. We solve for X by dividing by the 6. That would be running at 400 RPM. Make sense? Or a similar thing would apply for pulleys. If I have a 4-inch pulley meshing with a, let's say, 12-inch pulley, and this one here is running at 360 RPM. To find the speed of that 12-inch pulley, it's 4 times 360, has to equal a constant. Well, the other one would be 12 times X. 4 times 360 would be 1,080. And then, is it 1,000? You're right. 1440. I was doing 3. Nice catch. That is 1440 divided by 12. Is it 120? So this is 120 RPM. It makes sense. The size of the pulley is 3 times the size. The RPM is 1/3 the RPM. Let's say a pump, a 9 CFM pump, takes 30 minutes to drain a tank. How long would a 12 CFM pump take? So a bigger pump, is it going to take more time or less time? Less. So the pump gets bigger, the time gets smaller. Again, inverse variation. So it's the size of the pump, 9 CFM, times the time it takes, 30. That has to equal a constant. So the other pump, when it was a 12 CFM, we're looking for its time. 9 times 30 is 270, equals 12x. We'll divide by the 12. 270 divided by 12 is that 22.5? Minutes. So the 12 CFM pump takes 22.5 minutes. So in your book, page 294, exercise 7.3 deals with direct variation. Page 297, exercise 7.4 deals with inverse variation. So I'll let you work on those 2 pages for Tuesday. Only a couple more days of lecture left for all this, huh?